In this video, we're going to talk about magnetic matter, like permanent magnets, in a very simplified way, so forgive me. The main thing to emphasize here is that atoms are made of a nucleus, which is their positive center, and they're surrounded by electrons, which are negative. And one way to think about it is as the electrons kind of orbiting around the nucleus. Now this is wrong, but it's a useful way to think about it. And if you think about an electron, well, it's charged. If you have it moving around in a circle, well then you've just basically created a current loop. And we know that current loops produce magnetic fields. And in the same way, we can say that an atom can have a kind of a north and a south magnetic pole, which I've drawn here. Now, most materials, those kind of north and south poles of the atoms are kind of randomly oriented in the material. So that's what I've drawn here. And in most materials, which are called paramagnetic materials, the magnetic fields produced in an atom are very weak, right? So an individual atom makes really kind of a negligible magnetic field. And the fact that in a larger material, they're all kind of randomly oriented means that any magnetic fields they had would kind of cancel out and you end up with no net magnetic field. Now, something to remember is that if we put a magnet into a magnetic field, so say we have a magnet here and we put it next to this magnet will spin, so its poles will line up with the magnet down here. And you can think about that as the south side here just being attracted to the north side here. So it's going to spin to align. Well, the same thing will happen in paramagnetic materials. If we put a strong magnet below, a lot of the atoms' poles will kind of tend to align a little more. And so, and different paramagnetic materials will do this to different extents. So some materials there's really hardly any change, and others there will be a significant shift in the kind of direction of the poles in the atoms. And if you get a particularly good paramagnetic material, they'll line up to some extent. And now that they're lined up, the magnetic fields will add to create a net magnetic field. So that we could even say that this paramagnetic material here could have a north and a south pole, albeit very, very weak magnetic fields produced. And when you remove that permanent magnet from below, these poles will tend to kind of randomly orient themselves again. So it'll lose its magnetic properties. So another class of materials are called ferromagnetic materials. And this includes stuff like iron. And permanent magnets, so like the magnets you would have on your fridge, are made out of ferromagnetic material. And one big difference between paramagnetic and ferromagnetic materials is that the magnetic fields produced by ferromagnetic atoms are, the fields are much stronger. So they just have a stronger kind of north and south pole than paramagnetic materials. They also tend to align with each other so that in a material, so I've kind of drawn one here, and I've kind of outlined in purple, they are what's called domains. And domains are just kind of areas where the atoms are all kind of pointing their north poles in the same direction. And again, they're kind of randomly oriented. But if you put a ferromagnetic material in a strong magnetic field, like I've done here, there's a much higher degree of alignment than in paramagnetic materials. So here I've drawn it so that all of the domains are now lined up with the magnetic field of the permanent magnet down here. And this will give it a strong net magnetic field so that it'll have a north and a south pole, and it will also have pretty strong magnetic properties. And again, that's just because they align a lot more than paramagnetic materials and that their magnetic field is kind of inherently stronger. And permanent magnets are ferromagnetic materials that are generally locked into place so that the domains are all oriented one direction. And dropping them or heating them up kind of makes them kind of spin off into other directions, kind of breaking down the magnetic properties. So if I get a permanent magnet, as I've drawn here, and I put it on a ferromagnetic surface, it'll make all those poles in the ferromagnetic surface line up, which will give it a kind of a temporary south and north pole. And that's how you can get, a magnet to stick to iron or something. The same reasoning holds for acrobats. So we had a north and a south magnet, and we had aluminum acrobats, which are paramagnetic. But the poles aligned enough that they became weakly magnetic so that you could stack them on top of each other. And that's magnetic matter.